Good morning, everyone. This paper is titled Accelerating Performance Inference over Closed Systems by Asymptotic Methods, which was presented in ACM Sigmatics 2017. The goal of this work is to revisit the computational theory of closed queuing networks, which have been extensively studied since the 70s. In these models, there is a population of n jobs which cycles through a set of nodes receiving service at each node, possibly after some queuing. In this diagram, which represents a closed queuing network, you can see a set of queues and a so-called infinite server node or delay server where jobs do not queue, they just receive service with average service time sigma r. Conversely, the average service time at a queue I multiplied by the average number of visits to that queues gives us another of the model parameters, which is theta IR. R here represents the class of the job, so the type of the job. You may see here in different colors that jobs of different types can be considered in these models. We call NIR the number of jobs of class R that are visiting in a given state station I. So throughout the presentation, we consider the special case where sigma R is equal to 0, so there are no infinite server nodes, but our paper covers also this case. And so to recap, there are k nodes in this model, R classes. Each class has a population of NR jobs that cycle through the network, and the routing here can be probabilistic, but these probabilities will determine the average visits to the resources which are already incorporated in this service demand theta IR, and the total number of jobs is n. Now, there is a classic result from so-called product form theory of these models, which is that the joint probability distribution for this model at equilibrium has the expression of a product of multinomial terms with parameters given by these demands theta IR. Ni here represents the sum of all the NIR jobs at station I, so essentially the total population of jobs at I, and the quantity G here represents a normalizing constant that ensures that this probability expression sums to 1 when you sum overall set of possible states for these models. And because of this last observation, the normalizing constant can be written simply as a summation of a raw state space of the same multinomial terms we have seen before. Now, obviously, this term is very difficult to calculate exactly because there is a combinatorial explosion. The number of states of this model as the number of jobs, nodes, and classes grows. And in this paper, we try to revisit exactly this problem. And to give you a sense of the kind of applications that can benefit from better methods to analyze the normalizing constant G of the state probabilities, consider, for example, the problem of inferring the service demand theta IR from measurements. We might, for example, have collected recordings of empirical mean queue length for a given system that can be modeled as a closed queuing network, and then we might set up a maximum likelihood estimation problem to determine the value of the demand theta IR that fits these observations. If you do so, you will end up observing that the normalizing constant appears in the objective function of this MLE problem. And then normalizing constant, even though not put explicitly here in the slide, depends on the variables of the optimization theta, and therefore it needs to be re-estimated every iteration, which is computationally quite demanding. If we try to apply methods to estimate the normalizing constant G that have been proposed in the literature, either exam methods like the combinatorial algorithm, recall, the method of moments, or various kinds of approximations like Monte Carlo integration, Taylor expansion, the array method, and so forth, we will find that, particularly if we bound the execution time to be fast, for example, 60 seconds, and we interrupt the execution of the method, we see that what we obtain as a result is a solution that is inaccurate generally. So even if we remove from the optimization program the normalizing constant, we work therefore with an approximate objective, the results are way far from optimality. So here essentially we let the different iterations of the MLE problem run for 60 seconds on models with 3 nodes and 3 classes and 120 jobs, and we evaluate the percentage error of the obtained solution in terms of objective function compared to the real value of the objective at the optimal point. So this means essentially that unless we can find better ways to evaluate the normalizing constant, it is difficult to find good solution with these objective, with these optimization problems. And to tackle this problem, we might observe first a connection between the theory of closed-query networks and the interpolation theory, which have not been observed before. So consider, for example, an arbitrary function f of x, which is measured at data points, also called nodes, theta 1 to theta k. Now, this function can be interpolated at these points using Newton's interpolation polynomial, using the expression you see here, where the coefficients of the expression are the so-called divided differences of f of x. When we look at these divided differences, they have a known closed form expression, which you see here. They are essentially summations of the function evaluated at the nodes, scaled by the products of the differences of the nodes. This observation is relevant to closed-querying theory because when we consider the particular case of a closed-querying network with a single class of jobs, we can see that actually the known closed form expression for G in this case takes a form that is a divided difference, provided that the function f of x that we consider is a power function. So we can rewrite here G as the divided difference of x raised to the power of n plus k minus 1, where, as you might remember, n is the number of jobs in our model and k is the number of nodes. And so we have established now a connection between interpolation theory and closed-query network theory, which was not known before. Why is this interesting? Well, because in interpolation theory there are some results for divided differences which have not been used before in closed-query network theory. For example, we might consider the Hermite-Janoky formula for divided differences, which allows us to express a divided difference as an integral over the k-dimensional unit simplex, which in the particular case of the normalizing constant brings the new closed form expression for G in single class models that you see here. So it's an integral form over the unit simplex with k dimensions. So we are looking at points U where the sum of the components of this vector U are equal to 1 and they're all non-negative. And so in each point of this simplicial region, we simply evaluate a power of a linear form obtained by multiplying the demands θ1 to θk in a single class model by the coordinates at this point. So we carry out the integral, and there is also here a couple of factorial coefficients that allow you to obtain at the end the normalizing constant. There are other integral forms that have been obtained for the normalizing constant, for example, by McCann and Mitra in a JACM paper in the 1980s. And this can be related to our new form through a Laplace transform of the volume of the simplicial region K. And so there is a possibility to obtain the known form through a Laplace transformation of this new form. Now let's try to visualize this integral more precisely. So if we consider, for example, a simple model with two cubes, every point over the simplicial region will have coordinates u that need to sum to 1, and therefore one of the coordinates is linearly dependent on the other. Let's assume without loss of generality that the two q's have distinct demand. If they are identical, the model is trivial. And so in this case, we have that the value of the integrand over the unit simplex can be shown over a unidimensional plot here, because the other coordinate is dependent. And so you see how it looks like for different values of n. So in particular, it tends to concentrate around the corner here at u equal to 1 and u2 equal to 0, as the number of jobs increases. Now, it is not very difficult to show that this new form we have obtained actually generalizes to arbitrary number of classes. The main difference is that now, instead of considering a single power of a linear form as an integral, we have a product of powers, one for each class R. And also the factorial terms at the beginning need to be slightly corrected to take into account that there are R classes. And so this can be proved, for example, using the multinomial theorem. If we look at the initial expression for our joint state probabilities, that was dependent upon a product of factorial terms related to the total populations of jobs in the k nodes in that state, and that this product of factorials can be shown to have integral form, as you see here, as an integral of the unit simplex. So basically, if you expand by the multinomial theorem these products, using this relationship, you can recover the product form expression we have shown at the very beginning, which ends up matching the definition of G. And now, using this integral form over the unit simplex, we can derive a number of computational algorithms, either exact or approximate, for the normalizing constant. So we will start in particular by looking at explicit solutions for G. So we look at explicit expressions that do not involve an integral, but there are simple algebraic expressions. So to recap, we have obtained for single class and multi-class models these two integral forms. Now, we might wonder how they are related, why we were able to obtain this multi-class generalization. Well, it turns out that if you look at the power of the linear form in the single class case, you can obtain a formula similar to the, actually matching exactly the one, the multi-class case, by taking derivatives with respect to an artificial parameter t that you introduce for different classes. So Tr is a dummy parameter for class R. And therefore, we can see with this relationship that basically, if we replace the product, Mr. Beck, in this integral here, the product of linear forms in the multi-class case here, with the partial derivatives here, we can make the integral become as in the single class case, with a single linear form raised to a power n. You see here, this is on the right hand side, a single linear form with the power n. And so this means that we can transform the multi-class integral into a single class one, provided that we introduce dummy variables, and working out the resulting expression, which involves derivatives. We can show that these derivatives can be replaced with finite differences. And this implies in particular that we can give an explicit form for the multi-class normalizing concept that you see here, where the inner term on the inner summation, you see there is an outer summation over the values of these dummy variables. The first term relates to the finite differences, which we have used to replace the derivatives. I point to the paper for details. But also there is, on the right-hand side, the explicit closed form solution for the single class model case. And here the theta's are obtained by weighting through these dummy parameters the multi-class demands. So essentially, this is an expression over the values of these dummy parameters that involves all the parameters of the multi-class model. It can be solved exactly, but it might have numerical difficulties because of, for example, these binomials and the alternating differences here, and therefore it needs to be evaluated using, for example, exact algebra. And so one benefit of this exact formula compared to the literature is that it requires constant space, because you can compute every term without having to memorize any previous term in this summation, and therefore you just accumulate these terms in your counter that then gives you at the end the normalizing constant g. So it's O1 space. The computational cost in terms of time complexity is identical to the convolution algorithm, as it depends primarily on the product of these nr plus 1 cases in the outer summation. So it's essentially growing exponentially with the total number of jobs in the model. We were able also to show that this, in the paper, that this exact formula can be rewritten as a summation over vectors h that are k dimensional, where k is the number of nodes. These vectors are constrained to have modulus less than the total number of jobs n. But again, you have an exact expression that you can compute in O1 space. But the computational cost of this formula is different from the one of the previous slide, and it matches in particular the one of the recall algorithm, but contrary to recall, as O1 space. So recall is a method that explodes combinatorially with the number of nodes your model. So it's more efficient with models that has many classes. Let's move now to asymptotic expansions of our integral form. So what we do to evaluate a large model with many classes and cubes is to transform our integral over the unit simplex using the so-called logistic transformation. It is very advantageous to have an integral over the unit simplex because the logistic transformation has been defined exactly the first place to map an integrand over the unit simplex over Rn, where n is the number of dimensions of the simplex integral minus 1, and to have this new transformed integrand over Rn as similar as possible to a Gaussian. And so after we apply this transformation to the integrand of our integral form, we obtain a Gaussian-looking integral over R the k minus 1, where k is the number of nodes in our model. And even for very few jobs, say 5 jobs, there's already a close similarity to a Gaussian. And this is extremely advantageous because most methods, for example, for sampling large multidimensional integral, benefit from having a unimodal integral that looks like a Gaussian. And so after this logistic transformation, we are indeed able to do this approximation that leverages sampling or asymptotic expansion and the similarity to a Gaussian. In particular, we can show that the mean of this Gaussian, so the center of this Gaussian, is a point Q that satisfies this fixed point equation, which somehow resembles the asymptotic form for large populations of mean value analysis. But this formula is also applicable in our setting to models with a finite population. And we give in the paper also an expression to calculate the covariance matrix associated with this Gaussian once you have solved this fixed point equation. And so at this point, we have proven formally in the paper that as you put the model in heavy load by increasing the total number of jobs, the normalizing constant will converge to a asymptotic form, which is shown here. We are showing in the slide a slightly simplified expression where we essentially set to 0 approximately the parameter epsilon of our asymptotic approximation. So in the exact expansion we have still term epsilon, but I'm showing how it will look the expansion if you set this epsilon equal to 0. And so you see that there are the different terms that relate to the parameters of this Gaussian, like the determinant of the covariance matrix of this Gaussian. And in this asymptotic expansion, which we call logistic expansion, we are assuming that there are epsilon n jobs which are added to the original model to impose the constraint that every station has certain a small fraction of the jobs that are perpetually looping around the station. Under this approximation to the original model, we can show that the model will converge asymptotically to this expression. So the motivating example we've shown in the beginning can now be addressed using this asymptotic expansion. It's quite remarkable to see how within those 60 seconds we find the optimal solution of our model within 1% accuracy using the new method we have proposed. We can show now another result based on so-called cubital rules. So let's go a bit again back to the integral over the unit simplex, and we consider, for the sake of illustration now, a model with 3 nodes, where therefore the simplex is over 3 dimensions, out of which one is linearly dependent of the other. And so this defines in particular a triangle over a 3-dimensional space. So one way of approximating the value of the integral is to sample the integral at particular points according to so-called cubital rules. So these rules give you a set of weights that you can use to weight the values of the function at these points to determine the corresponding value of the integral. And so the points are symmetric in their position with respect to the barycenter of this simplex, and it can be shown, in particular there is a paper by Goodman and Muller that show that a rule is exact for a polynomial, and this is the case of our integral, which is a polynomial, provided that it is of order s equal to the ceiling of n minus 1 over 2, where n is the order of the polynomial. And therefore, this means that approximately with computational cost of the order of n over 2 raised to the m, we will be able to assess the value of our integrand exactly to these Goodman-Muller cubital rules. If we choose an order that is smaller, the cost is lower, but the integral value will be approximated, whereas with this assignment, where n is the total number of jobs in our model, the result will be exact. And so we can show how this looks like in practice. So we consider here our example model. So if we look at a low degree cubital rule, we just evaluate the integral at 4 points and we get a large error on the normalizing constant. But as we increase the degree, we are using many more points. You see they are symmetric with respect to the barycenter that you see here at the middle. And the error already starts to decrease. If we go to a rule of order 4, with just 35 function evaluations, which is very fast, we have an error that is 6%. With 84 points, we are basically exact, and therefore we have solved our problem. And now what we've done is we have tried now a randomized solution of a randomized set of problems for maximum likelihood estimation. We had varied number of stations and classes between 2 and 32, requiring that the ratio between the total number of jobs and the number of classes is 2. So basically every class has 2 jobs. And what we see here is that these cubital rules that are tractable in these family of models are 58 of the times the best model to choose for the solution of the MLE problem. So for fixed time, they produce the solution that is the closest to optimal. And our logistic expansion, the asymptotic approximation we have shown before, is best in 32% of the case, and in the other case, the best action is actually to remove the normalizing constant. If we increase the population, it turns out that the asymptotic expansion is the best one, as one can show that the model can be analyzed exactly with that expansion as n is asymptotically large. Perhaps quite surprisingly, the second best method is to exclude entirely the normalizing constant from the objective function. And this is because it is known that asymptotically the model will start to converge to an open QE network, and therefore the removal of the normalizing constant in that case is provide a form for the probabilities which is matching the exact solution of open models. So in conclusion, we have studied the problem of approximating normalizing constant in single class and multi-class closed QE networks, and we have determined a novel integral form together with several exact and approximate solutions that enrich the range of tools available to analyze the closed multi-class QE networks. There are several other results which I didn't have the time to describe in this presentation. For example, importance sampling methods, which leverage again this Gaussian form over the unit simplex of the transformed integrand. We have also hybridated our approximation with MVA to determine the location of the Gaussian integrand. The theory has been extended to models with delays, and we report in the paper an extended validation on random models. Thank you very much for your attention.